Okay, so like I said, we're starting 9.4 here. This is this in the next section, the last two sections in chapter 9, and it's on the empirical mode decomposition. So the empirical mode decomposition is just an algorithm that extracts some what are nearly orthogonal components from a non-stationary, nonlinear signal. So when we say they're nearly orthogonal, there is a definition of orthogonality that you can find in the paper. We won't cover it in the notes, but what you need to know is that the components are not perfectly orthogonal to each other, like the basis vectors in the POD, or the temporally varying components in POD, in this case, which are perfectly orthogonal. In this case, these are not completely orthogonal, but they're close to being orthogonal. So EMD is applied to extract these nearly orthogonal components, which are then called intrinsic mode functions. These intrinsic mode functions are going to satisfy two conditions. First, that in the entire IMF, the number of extrema, that means max and mins, and the number of zero crossings must either be equal to each other or they differ by one at most, meaning that it's an oscillatory component that occurs at a single frequency. And that doesn't mean that that component or that frequency can't change over time. It just means that there's only one component or one characteristic frequency associated with the IMF at a particular time. The second condition is that the mean value of the envelope defined by the mean value of the envelope of the local maximum and the envelope of the local minima is 0. And that is really what is kind of a new idea that is introduced in EMD and serves as the basis for EMD. That first condition is something that's been well established, particularly for narrowband signals, particularly linear signals in general. And so in terms of signal processing, it's not really that new for the EMD. EMD is now like almost 30 years old, so it's not necessarily new. But in terms of what we've covered in signal processing in general, the first point is not that new, and the second one is the new idea that is introduced by EMD and forms the basis for it. So we have some oscillatory signal here. In this case, for this to be an INF, we're going to have that the envelope described by the maximum values, which I'm now drawing here in red, we can call that E plus T, that envelope, and then another envelope, which we'll draw on the bottom here, which is formed from the minima. You can call that E minus of T. Their mean value must be 0 locally. So they won't necessarily always be exactly 0 at a particular point in time, but in terms of a mean value, that will be 0. We can call that little green line that I just drew, we'll call that M of T. All right, and this condition here will need to be revised. Okay, sorry. Actually, it is right. So that M of T is 0, and it's the mean defined by the envelopes, but the signal or the IMF itself may not necessarily be 0 mean at all times. That's the key thing. So in this case, the mean value of this IMF that we're looking at, this M, comes from the E plus and the E minus. It doesn't come from the actual signal itself. All right, so the name intrinsic mode function is used because, well, the idea is that an IMF represents some oscillation that is embedded in the original signal, or a particular mode of oscillation embedded in that original signal. Meaning that a particular signal that has numerous components will have numerous IMFs embedded in on it as well. And the goal of EMD is that a single IMF will capture, well, okay, as written there, this is true. So EMD, when you apply standard EMD, each IMF will capture only one mode of oscillation in a particular cycle of that oscillation. And when we say no complex riding waves are allowed, that means there can't be any kind of carrier signals that are coming along with that. So the intention and what EMD does do, or can do in some circumstances, is extract a component that contains only a single frequency in a particular cycle. That doesn't necessarily mean that the IMFs need to be narrowband. They can both be amplitude and frequency modulated, or they can even be non-stationary. And an example IMF is shown down on the bottom here, which comes from the original EMD paper, which is, like I said, almost like about 25 years old at this point. All right, so what I want to talk about is how we apply EMD. Then I have some pictures of how that process works, and then I'll show you some examples of what an IMF looks like when this process is applied to a signal. Okay, so EMD is applied through a sifting process that assumes the following. First, signal has at least one maxima and one minima. This is pretty much always guaranteed when we're studying some type of oscillatory vibration signal. If your signal is non-zero mean, then you can subtract the mean from that, such that you end up with multiple minimas and maximas about zero if you want. You don't necessarily have to. EMD will extract out, well, the final IMF, or what's known as the residual, actually will represent that mean. So you have that option as well. So at least one maxima, one minima, which is we're pretty much always going to have. Then there's some characteristic time scale that can be defined as time lapse between the extrema itself. Given that we have many oscillations in a vibration signal, that should be relatively easy to do. And then the third condition is that if there are no extrema, minimums and maximums, and it only contains inflection points, then those extrema could be revealed by differentiating the signal one or more times. In our applications, our signals will always satisfy the first two, and we'll never have to deal with the second or the third condition. So for a signal x of t, the EMD applies a sifting process that follows the following steps. We're going to start with our signal x of t. We're going to compute the positive and negative envelopes based on those maximums and the mean of their value. And just so you know, the mean, or m here, m1 is what I've written. This would be defined as m1 is equal to e plus e minus divided by 2. So just your standard mean. If that mean value is 0, or in practice is less than some tolerance that you set, then you just stop. You've already found an IMF. In fact, what it tells us is that your signal x of t is itself an IMF. And in which case, it's not really that interesting to apply EMD anyway. So most likely, it's not going to be an IMF. And in that case, we're going to let H1 be equal to x of t minus that mean value, M1 here. And we're then going to repeat steps 1 and 2, but for H1 instead of x of t, which will then produce H1, 1. We'll then repeat that again and get H1, 2, so on for as many iterations as we need to until we finally get something H1k and M1k, and M1k is equal to 0 or is less than or equal to some tolerance that is set in the algorithm. So once we've repeated these steps and extracted an H1k, that has this mean value of 0 as defined by the envelopes. We will then call that the first IMF, and generally IMFs are represented by with the C, so C1 of t will be equal to H1k of t. Once we find our first IMF, we then compute a residual, this is R1 of t, which is simply the original signal minus the first IMF. And then we'll repeat steps 1 through 4 on R1 to get the second IMF, C2. We'll then compute R2 of t, and then apply steps 1 through 4 on R2 to get C3, and so on, until we extract as many IMFs as there are in the signal. So there may be more IMFs, or EMD may extract more IMFs than there are actual components in the signal. We will see an example later on where there's only 2 components in a signal and EMD extracts like 8 IMFs. And then we'll see how the wavelet bounded EMD can overcome that kind of issue. All right, so after doing this sifting process, and you'll never do this manually, there are tons of codes, and you have codes already that came with the modal toolbox that do this for you. Actually, hold on. I think I'm going to have to give you guys another code that I forgot to share, actually. You have everything you need for the wavelet bounded EMD. If you want to do original EMD, I'm going to have to give you something. So anyway, at the end of this sifting process, we end up with some n minus 1 IMFs, which will hopefully reproduce and be representative of something physical that's going on in the original signal, and 1 residual signal Rn of t, which is not an IMF. It does not satisfy the conditions of what an IMF is. That's why it could be something like a mean value from the original signal, or just some kind of constant value or some signal that has no oscillations in it. And by doing this, we can then reconstruct our original signal x of t as being equal to the summation of n minus 1, summation from I equals 1 to n minus 1 of our IMF ci of t, and then plus that residual Rn of t. So generally, what you'll find is that the residual is very low amplitude, or, well, ideally it's something that's low amplitude with virtually no oscillation in it. And as a result, you can then reproduce the signal by only summing up the IMFs. The same kind of way that you, in the last worksheet, you did that truncation with the POD, and you kept only a subset of the palms and their temporal variations, and you were able to reconstruct the dominant behavior of the signal, or the dominant content of that signal. Same thing here. The IMF should capture the majority of the behavior, and that residual should be relatively small. So the IMFs are organized from highest to lowest frequency, which is the opposite of the way modes of vibration are organized, which are more, in that case, they're organized from lowest to highest frequency. So you'll often see in an application to vibrations, the order of the IMFs will just be reversed, such that we can talk about IMF 1 being representative of the first mode of a particular system. It just makes that easier. All right, so on the next page, I have just some example figures showing, in this case, we're looking at an A. At the top is our original signal. Beneath that is an example of this upper envelope and this mean value. And the lower envelope, you can see here how this mean value does not have it's not 0 everywhere, but it does, well, you can just see how it's defined. The signal itself has a 0 mean, using the standard definition of a mean for the signal, and using the mean based on the upper and lower envelopes, you'll see that it's non-zero, and yeah. What you then do is you take that mean, you subtract it out from the original signal, and that gives you figure C. So see here, this signal right here, this is our original signal, which we'll just call OS, minus that mean value above. That's what you get out of it. And so therefore you can see that this first IMF has a higher frequency than, well, the residual component below there. Residual is just the original signal minus that IMF, and in this case, looks like it captures the low frequency response. Another example, the figures are probably a little bit blurry. The quality where I took them from was not that good, so in this case we have a tone signal added to a chirp signal. Chirp is just starting at a low frequency and increases in frequency over time, shown here. To the right of this is this application of the shifting process, starting off with just trying to find that first IMF. This is the very first iteration in this case, and it results in the residual as shown below there. Here is what it then looks like when you apply the second iteration of that sifting approach. And that mean is starting to become closer and closer to 0. And after 8 iterations, you can see that now the mean is almost exactly 0. And in this case, it would be less than the tolerance that we've prescribed, and we would therefore claim that this is now the IMF, the first IMF. Okay. So you previously saw this signal, I think, in worksheet 5, where you were applying, I believe it was filtering to try and decompose it into different components. I have an example here where I'm just going to apply basic EMD algorithm and show you what the IMFs for this particular signal look like. So before we look at the IMFs, I want to just show you the code. All right, so I got a bunch of plotting stuff. Right below that, comment. This is how I'm applying EMD. I'm using a code that I'll share with you guys, and it's just simply plugging in and letting EMD do whatever it wants. And there are tons of other modifications that you can do with EMD, and this is just the simplest approach, the simplest implementation of it, which will mean that it may work, it may not work sometimes. In this particular signal, it does actually do a reasonably good job. Looking at the first IMF, shown there on the left, you can see that overall, this first IMF captures the highest frequency component. There is a little bit of the second component popping up right here. That's something we call mode mixing, which we will go through in the next little subsection. IMF2 here is able to capture that oscillatory component like we mentioned, like we can see right there. And then IMF3 just captures that low frequency component in general.
So what does this do for us that filtering doesn't?
Yeah, we're going to get to that at some point. We're going to get to that next week when we go over the physics-based explanation for this method. And we will then use it to find internal resonances in data that link up to, that are mathematically backed up via the averaging theorem. That's what we get out of this. There are also times where filtering will fail. Now, that being said, EMD is a kind of filter, actually. It has been shown to be like a successive filtering approach, effectively. So, but instead of doing like a convolution integral, you're doing this sifting approach. Okay, any other questions? Okay, let's talk about this mode mixing issue. So although EMD did pretty well before, it often suffers from an issue known as mode mixing, which is where a single IMF will capture multiple components rather than only a single component. This is caused when either a component is intermittent, which means that it exits the response before the end of the measurement, or some of the components are closely spaced, which is defined as their frequency ratio being less than 2, although you can have mixing when it might be a little bit higher than 2 as well. All right, so like I said in that example 3, there is slight mode mixing. We're now going to look at an example where we'll have a lot of, extreme mode mixing. So basically, I've just taken that signal from example 3, and I've added here an additional component at 120 hertz. Just another sinusoid at 120 hertz without any time-varying content, like frequency content. You can see the signal on the right, along with the wavelet transform and the Fourier transform. And we're just going to apply the regular EMD and take a look at what that looks like. Here's what you get. The first IMF actually now captures the first 2 components in there. And then as a result, the second IMF now has other components captured into it. So in fact, also, this first IMF has this component here. That's actually just a numeric artifact. That slight gray one is not even real. It doesn't represent anything physical. We got mode mixing in the first 2 IMFs, and as a result, we have mode mixing in the third IMF, and then the fourth IMF doesn't really have any mode mixing, but it is missing part of its response. Okay, so we'll take a look at another example. This example, I don't have any code for it. In fact, you're going to end up studying this system or the data from this system in the worksheet we're going to do today. So we're just going to consider our beam. The parameters are just steel, and it's kind of a standard beam. The length is around 1 meter or so. It's got a cubic spring at the far end, and then an impulse is applied to that free end as well. The response shown on the right here is the displacement of that free end, and then beneath that is a wavelet transform from 0 to 200 hertz, and on the right is that wavelet transform from 0 to 50 hertz. Just so you can see these 2 components in here. So applied the regular EMD to this signal, and in this case you end up with, in the first IMF, which in this case they've been reordered, so number 4 here is technically the first IMF, but we've reordered it to align with the modes of the system. You can see that there is a mode mixing shown here. When I say intermittency, you can see that, let me erase that. You can see that right here, that component dies out, exits the response, and then suddenly this next component becomes dominant and is not captured in that IMF. When ideally what we would prefer is to have no content below like 50 hertz in this IMF for it to capture and really represent the response of that mode. You can also see that in the amplitude of this system where we start low, it jumps up, and then it jumps up again. And that's just representing this mixing that occurs. And then this then propagates down through the rest of the IMFs as well. And by the time we get to the first IMF, which you would hope would be representative of the first mode and therefore be the most dominant component, actually has almost no response in it as a result of this mixing. Okay, so I said this is common when the frequency ratio between 2 components is less than or equal to 2, and that is a very common thing that occurs in real structures, particularly because real structures will tend to have, they have an infinite number of frequencies, and eventually the gap between frequencies is just too small for them not to mix. So that being said, if you're dealing with a vibration signal, you will probably always run into this issue with the EMD. Okay, so let's talk about how we overcome the issue of mode mixing. And so there are many different methods that claim to fix this. In my experience, there's really only one that works, to be honest, and that's the use of masking signals. that works almost universally, I'll say. So that's what we're going to talk about, masking signals. So the idea behind using a masking signal is that we effectively just want to trick the EMD into mixing the component that we actually care about, the physical response, and mixing that with some known sinusoidal. And then once we get back an IMF that's mixed with that known sinusoidal, we can then extract the known sinusoidal and get back the IMF or the component we actually want. All right, so the basic process is as follows. We can consider some signal x of t that has, in this case, just two components, one at omega 1 and omega 2, such that they satisfy the condition omega 2 over omega 1 is less than or equal to 2. And then what we'll do is say that z of t is equal to big A times the sine of B times omega 2t, where A is just some real number and B is greater than 1. So in this case, the sinusoidal has some frequency that is above omega 2, but should still be pretty close to omega 2. From there, we're going to perform EMD on the signal x plus z and x minus z. We'll then obtain two mixed IMFs, C plus and C minus. And then using those two, we can obtain the actual IMF as C1 of t is equal to 1/2 C1 plus of t plus C1 minus of t. And this combination gets rid of that mixed in sinusoidal signal that we've added into the original signal. And you can then repeat this process to extract additional IMFs as needed. So the problem with this is what should A and what should B be equal to? And that is the real struggle, to be honest. So if you want to implement this approach, you will have to just guess A and B and manually iterate until you get somewhere. And doing this manually can take on the order of days to months to extract good IMFs.
How sensitive is it to changes in A and B? Like, can I just do a for loop that holds A and changes B by like 0.1 and then hold B and change A by 0.1 or something?
I mean, you could, but when you've got to extract 8 of them, 8 IMFs, and you need to do this 8 times, you've got 8 Bs and 8 As, and the last A depends on the performance of the first A and all the way through the chain. What are you going to do then? So the solution is to use an optimization routine, and in order to do that, you need some type of objective function or some type of metric. And we're now going to discuss on how that is implemented, and it's done through a method that's known as the wavelet-bounded empirical mode decomposition. Okay.
So how can you be sure that, it may take time, but how can you be sure that you finally find something? I mean, is
You
there a
can't.
guarantee?
No, there's no guarantee. So, right, so anyway, we're going to use a better tool than just masking signals alone. We're going to use the wavelet-bounded EMD, and we're going to discuss how this method works in order to optimize the extraction of components. Okay, so the wavelet-bounded EMD combines wavelet transforms, Gaussian windows, and just optimization to identify an optimal masking signal that will separate closely spaced components into IMFs. In order to go through the wavelet-bounded empirical mode decomposition, we're going to have to talk about what's known as the maximum wavelet transform. And so the maximum wavelet transform is just a projection of the wavelet transform onto the frequency domain, and this provides a smooth representation of the frequency constant, and that's kind of a key aspect here. So whereas something like a Fourier transform gives you a non-smooth representation, you get these jagged peaks, this maximum Wavlet transform is going to give us a very smooth representation. At the bottom of the page, you'll see an example, which we'll talk about in a moment. Okay, so the maximum Wavlet transform is simply going to be defined as, we'll use a tilde x of omega is equal to MWT applied to a signal x of t, which is then equal to the maximum value across time of the integral from minus infinity to infinity times psi bar sub omega t, that's our mother wavelet function, tau d tau. And everything inside that square bracket is simply the continuous wavelet transform. So basically, I'll scroll up a bit here. We're taking the wavelet spectrum. So what you've typically seen is just a 2D representation of the wavelet transform, but you can plot it as a three-dimensional spectra as shown here. And basically what the maximum wavelet transform does is that at each frequency value, it asks what is the maximum amplitude across all time, and then it just stores that value. And then you end up with things like what's shown on the right here, this maximum wavelet spectrum, which tells us where these dominant frequency content is across all time, and it ignores things like intermittency in the signals as well. And in this case, we get this nice smooth representation, like I mentioned previously, rather than a sharp, jagged representation. And so if you're wondering, in this case, there would be some component here, 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 and here. Those would be what we would consider to be individual components based on the MWT. Okay, so kind of the core observation of the wavelet-bounded EMD is that a well-separated IMF is going to have some type of relatively narrow band content in this MWT spectrum, whereas a poorly separated IMF will be broadband, meaning it will have many components and it will have a wide band. And here you can just see the MWT for a poorly separated IMF as well as a well-separated IMF shown on the right there. So with the poorly separated IMF, you can see that it has multiple peaks that appear, each representing a different component, and it's not necessarily very narrow band. In the case of the well-separated IMF, it really only has one particular peak. There is a little bit of contamination down here, although that is less than a tolerance that's shown here, that was specified in the wavelet-bounded EMD. All right, so based on this observation, the core idea of the wavelet-bounded EMD is to just basically bound the content of an IMF around a particular component using a Gaussian window or just a Gaussian function. And we call this process wavelet bounding. And so by doing this, the idea is that we can encapsulate the frequency content of that IMF inside of a Gaussian function and then compute the area underneath that Gaussian curve, and the value of that area, it acts to quantify the degree of separation of an IMF. And so if we do that for the poorly separated IMF, and you can see here that this Gaussian has to bound all of the content in the maximum wavelet transform, hence why it intersects over here and up here. As a result, that is a relatively large area, whereas on the right here, it will intersect over here, and then it intersects right here. And so on the right, the area is going to be smaller than the area on the left, and this then allows us to kind of quantify that. And then this serves as our metric for optimization. The goal is to minimize B by optimizing the masking signal that we use. Okay, so B here is large for a poorly separated IMF. And then over here, B is small for well-separated IMFs. And it's relatively small in comparison. Okay, and like I said, the idea of the wavelet-bounded EMD is to optimize a masking signal such that the resulting IMF is well separated as measured by that area B. And this wavelet bounding technique could be applied to other methods, such as variational mode decomposition, potentially dynamic mode decomposition, and others as well. All right, we're going to talk about just the application of this WBMD. So in the modal toolbox, you have the WBMD code shown here. It requires 5 inputs. The first is just a time vector. The second is a signal. That could be a column vector, or it could be a matrix where each column represents one signal. And then the minimum frequency and the maximum frequency within the range that you want to study. That includes all of the content you're interested in. And then you have to pass it a cell of characteristic frequencies. And this is what it uses to try and extract. So I'm going to back up a little bit here. We're going to go right here where I drew these. We'll go here. So when I say characteristic frequencies, you will look for at the wavelet transform as well as this MWT, and what you'll look for is peaks like this, and this is where you get this what your characteristic frequencies are. So in this case, we'd have some like omega 1, 2, 3, 4, 5, omega 6, 7, and 8 here. And this is what you're going to pass into the wavelet-bounded EMD to look for this. So you, in general, want to try and find these peaks as best as you can. The algorithm actually one of the things that it does is it starts off, so in this case, I think this is like 1200 hertz, that far limit. You would tell it that the range for calculating the wavelet transform is 0 to 1200 hertz. And what it will do is extract the first component and then decrease the maximum value of that, decrease the range of that domain once it, okay, let me rephrase that. Once it's extracted this omega 8 component, it will truncate the wavelet transform spectrum down to maybe like 800 hertz and then find the next component. What that means is that the exact frequencies where a particular maximum value occurs is going to change as the WBMD works. And so it uses what you provided as a guideline to search within a range, search for the maximum value instead of exactly what you've given it. So that being said, you do not need to be too worried about how precise you are in giving it a maximum, giving it a value here. It just needs to be within the ballpark, within the range of what's shown here. Okay. And you're going to do this in the worksheet. And then what it outputs then is a cell with all the IMFs. This can be done for multiple signals, so it will produce, so the value n here, this is your signal counter. So if you give it 3 signals, that will go up to 3, and then m is the number of components as well. One other thing I'll mention here is that each signal might have a different number of components that you want to extract out, and you can define this characteristic frequency cell in a way that they don't have to be all of the same. You don't have to extract the same components out of each signal. Okay. Like I said, you're going to play with this code or this function in the worksheet, and you'll get to see how it's used there. And in this case, we're just going to consider a simple example here. We'll just say y of t is equal to the sine of 2 pi f1 t plus the sine of 2 pi f2 of t, where in this case the two frequencies are closely spaced, and we're looking at time from 0 to 10 with the sampling frequency of 8,192. We want to decompose this signal using EMD and the wave bounding EMD, and then compare the number of IMFs extracted using each method. We'll then plot and compare the IMFs with the underlying components, which is what we've got on the next page shown here. So for the first part, I just show you, here's the code. First one, first section here, we are creating the signal, defining the minimum maximum frequencies, and then defining this characteristic frequency vector. Beneath that, we're applying this we're applying EMD to the signal, and then we're applying the wave bounded EMD to the signal, and then just comparing the size of these. And that is the output here. You can see that the EMD gives you 8 IMFs, although there's only 2 components in the signal. And, well, the wavelet bounding EMD will give you 2. The wavelet bounding EMD gives you as many components as you tell it to. Whether or not it extracts something physically meaningful or not is a different story. So it does involve you being aware of the frequency content, being able to understand and analyze that, and choosing good characteristic frequencies. Okay, let's take a look at what the IMFs themselves look like. So I started with that second component because the first IMF here represents the high frequency content. We'll just zoom in here. You can see that the first component shown there, high frequency in terms of the wavelet, and in the wavelet transform of that IMF, you'll see here clearly that there is mode mixing. We have 2 components showing up despite, the goal of EMD to extract a component that has only 1 frequency in it. The other thing I'll say is that the components are not intermittent, so this is a mode mixing caused by that frequency ratio. We take a look here at the IMF extracted using the wave bounded EMD. You'll see here that it is almost identical to that component. There are some end effects. This can be fixed with mirroring, which is not implemented yet, not implemented in the version of the code that you guys will have access to, but those end effects could be addressed with mirroring. In this case, it's nearly identical, so that is a good sign. If we go and take a look now at trying to reproduce that first component, you'll see here that when we look at just EMD, although the signal does have kind of the same frequency content, it is substantially smaller, about half the amplitude of the actual component, and this is seen in both the time series and the way of the transforms as well, although it does not have any mixing in its components because it tends to happen with highest frequency mixes with the next frequency. If we take a look here at the extraction using the wavelet bounded EMD, it does a much better job of matching that amplitude. It's not perfect though. It just is representative of what's going on there, and it does not have any mixing involved there as well. Okay. Got one more example. So we're looking at this beam again. On the right, it's just the displacement and the wavelet transform, and beneath that, there's a maximum wavelet transform up to 200 hertz, as shown here. It's a little bit cut off, that label there, and we're simply using wavelet bounding EMD to extract the components shown here. Oh, whoops. There. So here you can see there is the fourth IMF is content only at somewhere around 130 hertz. Beneath that, the third IMF will only have content between around 75 hertz, and so on as we go down. The other thing you'll notice on the far right, that is the maximum wavelet spectrum. In light gray is the original signal. In black is the MWT of the IMF itself. And so here you can see how the IMFs reproduce that MWT content of the original signal.